Today we're going to start with continuing where we left off last time. So remember that last time we did not have time to write an efficient task parallel code. So we wrote the first version of our heat transfer solver, but it was very slow. So we're going to continue that. We're going to optimize it. And then we'll probably spend the first half an hour on this. And then we'll jump to part 3, domain parallelism, and we'll talk how we can run data parallel codes in Chapel, both on a single node and on multiple nodes with lots of examples. So let me get back to the code. So actually, let me first forward to the slides where I show the domain decomposition that we do with task parallelism. So we divide our domain two-dimensional domain, which is a matrix 100 by 100 mesh points, into these 3 by 4 blocks, so 12 blocks in total. And each block is assigned to a separate task. And then each task basically goes through a set of row indices and through a set of column indices, and then solves the time-dependent heat transfer equation. So this is the code that we ended up last time, more or less. So I did some small edits, but more or less this is the code that we finished last time. And again, if you have access to CEDA, you can always copy all codes from my CEDA directory. So here I'm on CEDA. And if you go into this directory, so actually let me type the full address. So home/Razumov/TMP. So this is the directory where you'll be able to find all the codes that I'm running live right now. So the code is parallel1.chap, this one. And here I'm showing it on the in the text editor on the left side of the screen. So what we're doing here is we initialize all our variables, and then here we have our domain decomposition. So we decompose it into 12 tasks, so 3 rows, 3 rows and 4 columns. And then we're computing indices. So we're computing how many matrix rows per task we have, and how many matrix columns per task we have. And then we also need to account for the fact that it might not divide evenly. So there's a remainder, and then we add the remainder rows and remainder columns to the last task. So we do it actually right here, where we calculate the range of indices for each range of rows and range of columns for each task to process. And then, so this is our task parallel loop, where we go through all 12 tasks, and then each task basically computes temperatures for a given range of rows and columns. So let me compile the codes again. And actually, so I wrote a make file, but when I write the make commands, you will see what command underneath it runs to compile the code. So I'm going to compile the basic serial code that we wrote 2 weeks ago. So I'm going to say make base silver. Oh, right. Of course, I need to load the environment. So that's good that I actually got this error message, because you can see how we load the environment. So the first thing we need to do is load the GCC compiler. And if you just logged into CEDA, and the single locale Chapel module. So we run this command, module load GCC chapel-single/1.15.0. So we're loading the Chapel single locale Chapel module. So now our Chapel command is actually accessible. So if you type chpl, then you will see what you will get a message showing all the possible flags for the Chapel compiler. So once again, this is the command we ran. Okay, module load GCC and then Chapel single module. And then we also want to start the interactive job, inside of which we're going to run all our Chapel commands. So the command I'm going to use today is actually very similar to the command last week, except that the name of the reservation is going to be different. So let me simply look into my bash history. So here's the command. I'm going to start to run the job. So actually, let me modify that. Oops. Let me modify that, and I want to start it for just to make sure I have enough time inside the interactive job to finish everything. So just start a 1 hour single node, 3 core jobs. So a number of NPI tasks is 1. Number of CPUs per task is 3, so we're going to run everything on a single node on 3 CPU cores. Memory per CPU, we're not going to run anything memory intensive, so I'm just asking for 1,000 megabytes per task. And then your account name, and again, for each one of you is going to be something different. So for me, it's defrazumov.ac, so that's my default allocation. And then reservation today is going to be cc-training_2, so different from last time. And when you run this command, if you register for the workshop, then I added everybody as of yesterday who registered for the workshop to the reservation, and your job should start soon. So depending on how busy the schedule is. Okay. And yeah, thing is, so somebody posted the link to the Google Doc that we're going to use today. So it's bit.ly/chapel3, and it's actually on the slides as well. So if I go back to the to my slides, I have way too many windows here. So if I go back to my slides, the notes, the shared Google Doc that we're going to use today is this one, bit.ly/chapel3. And this is the page where you can ask questions, where you can paste in your solutions, and basically anything you wanna ask or add, feel free to use this page. And also onto this page, I pasted the link to the updated slides. So the slides you see on the screen, you can download them onto your laptop. And at the end of today's session, I'm going to also add a link to the notes and the code. So basically, everything I say and show will be in my lesson notes, so you don't have to copy all the codes that I'm writing if you don't want to. But I'll try to go slowly, so you'll have time to write your own codes and test them. Okay. All right. So let's compile the base solver once again. Make base solver. So now the Chapel module has been loaded. We started the interactive 3-core job. And so the command is chapel --fast base solver.chapel -o, and then the name of the executable. And also I'm going to compile the Parallel1 solver that you see in my text editor on the left, and that all of you should have a copy of. And again, if you just joined recently, you can always copy this file from my directory on CEDA. So I'm working out of this TMP temporary subdirectory in my home folder, and the file is called parallel1.chapel. Okay. So now what I'm going to do is I'm going to run first a serial code, So base solver for the following problem. So exactly the same run we did last week. I'm going to run on a problem 650 rows and 650 columns. So printout point is going to be 200, so row 200 and column 300, and then the maximum number of iterations is 10,000. Tolerance on which we stop is 2 times 10 to the -3, and then we print out temperature every 1,000 steps. So let's just run it. And I also want to remind that we have the time counter inside the code. So we actually don't have to time the execution time from the bash shell. We have it the timer right here. So we have the watch start and stop statements, and then the difference between them is actually printed out right here onto the screen. So the simulation took 12 seconds, and this was a serial code. So let's now run the parallel code that we just compiled.
Excuse me.
Yep.
I wrote in the chat, but I cannot see the upper part of your screen, so I missed the reservation and.
You cannot see the upper part of my screen?
Yeah, it's like cat. I checked for control, but I don't have any. So I don't know if it's the same.
Can you double click on the screen
that you
see?
I did that. I did that, but it's still not changing.
Because we tested it before starting the seminar, and it actually worked. So I don't know what the problem is. I can restart screen sharing. So let me do this. But hopefully that solves the problem. But if not, then.
But can you tell what was the reservation? I use the same like.
Yeah, sure. So the reservation. Yeah, the reservation is exactly the same as last time, except that number 1 we have number 2. So the reservation is, let me search for it. I have way too many screens here, so it's difficult for me to.
I will print it. I have it.
Yeah. So it is. So reservation name is CC for Compute Canada -training_2 today. Yeah, so Camille just pasted it into the chat window. CC-training_2. Okay. So I'm going to run the parallel code now. And because I'm running this as part of an interactive 3-core job, the task parallel part will run on 3 CPU cores. So it should be, ideally, it should be faster. So when we run it, we actually see that it's progressing slower than the serial code. So the serial code took 12 seconds, and the parallel code, let's see how long it takes. For the same number of iterations, so 7,750 iterations. The parallel code actually took 23 seconds, which is almost twice as long as the serial code. And we ran it on 3 cores, so it should be ideally 3 times faster. So we definitely have a problem here. We wrote the first version of the parallel code, but it's not performing very well. So the question is, what caused this problem? So those of you who reviewed the lesson notes from the previous week, you probably know the answer already because it's in my notes. But if not, then I will tell you now. So let's take a look at the code, our parallel code, which is on the left screen. So what we're doing here, we're initializing all our variables, and then we are starting the time-dependent iteration. So basically, the counter starts from 0, and then we're incrementing it. Where it is, the increment count +1 right here. We're incrementing it by 1, and then so inside each iteration, time iteration, we are subdividing our problem into 12 tasks. And so we're actually starting 12 tasks on 3 cores. And then we're doing calculation of temperature for 12 tasks, initial of the 12 tasks. Then we finish these tasks, and then we calculate delta. Here we're doing this using data parallelism. And then we're assigning the assigning the new temperatures to the older array T, and then we optionally print out the temperatures, and then we're iterating once again. So basically what we're doing here, we're starting 12 tasks at each iteration loop, and then we're computing temperature in parallel, and then we terminate these tasks. And because we have almost 8,000 iteration loops, so we're actually breaking into 12 tasks almost 8,000 times. And there's a lot of overhead with starting and finishing threads on CEDA. So it's a certain number of microseconds, and because we're doing it so many times, this is actually why the code is so slow, because we didn't write an efficient code. So our code breaks into multiple threads 8,000 times, and then 8,000 times it terminates these threads. So what I have to do is actually make sure that we start the threads only once, and then we do time iteration inside these threads. So we need to make several modifications to the code. The first thing we're going to do is we're going to take this code-for-all loop, where we go through all 12 tasks, and for each task we calculate the starting and ending indices of the rows and columns that the task processes. And we move it just before, so the thing I highlighted on the screen, we move it just before the while loop. Okay, so we take it and put it right here before the while loop. And also the closing bracket, curly bracket, this one, we need to make sure that it goes right after the end of the while loop. So let me just highlight the new nested loops and make sure that I have the proper indentation. Here we go. So here we started, now we're starting the code-for-all loop, and then we're calculating the starting and indices, starting and ending rows and columns for each task, and then we're starting only then inside we start the while loop, right? So now the while loop actually started inside the code-for-all loop. So now we also need to modify the place where we assign the newly computed temperatures to the T array. So here where we update temperatures. So now this while loop runs not on the full set of rows and columns for the entire matrix, but it runs for each task only from row 1 to row 2 and from column 1 to column 2. So when we do this assignment, we actually need to make sure that we are processing the right block. So here we're only assigning mesh elements from row 1 until row 2 and from column 1 until column 2, right? And the same on the right-hand side of this assignment. So TNU has to be one of those indices fall into that range, right? Okay, so this is not sufficient yet because we need to also synchronize the tasks. So if we run the code as it is, it's actually going to work, but it will not give you the right calculation, because what's happening now is here we're updating temperatures, we're computing new temperatures. Then when we finish computing new temperatures, we're updating delta, which is the biggest difference on on the entire mesh between the new temperatures and the old temperatures. Then we update new temperatures and so on. And we do it many times in a loop. But the problem here is that we actually need to make sure that we finish computing the new temperatures everywhere on the mesh, so on all tasks, not just on a given task. On all tasks, we need to finish computing new temperatures before we calculate delta. Otherwise, our calculation of delta might actually use some older temperatures. So we need to introduce a synchronization point right here between all tasks, because this loop is now running in parallel on 12 tasks. So I'll say sync point 1. This is where we need to have a first synchronization point, and then also need to synchronize after we after we update the temperatures right here. So I'm going to say sync point 2. Because after we compute delta and after we update the T array, we want to make sure that all processes pause here and make sure that all this calculation is done before we jump onto the next iteration. Right? Otherwise, we'll have a mixture in the array T, for example. We'll have a mixture of old and new temperatures, and this is just not good. So we need to insert two synchronization points. How do we do this? So in Chapel, there are many ways of doing explicit task synchronization. So there's the sync command. Remember sync keyword. You can use sync variables. You can use atomic variables. So we're going to use atomic variables for this. And I'm going to switch now to the code that we ran last time. So the code atomic.chapel. And in this code, I just remind you what we did. Here we have a synchronization point that is implemented via the log variable. So we have a variable log that is an atomic variable. Atomic means all processes can actually write to this variable, and all of them will succeed. But what happens to this variable? Well, it's dictated by the program. So here we define this variable. We set up the default number of tasks equal to 5, and then we write. So here we're still running on a single thread, single task before the call for all loop, and then that task writes 0 to this log variable.
Yeah, there's a problem with your screen, Alex. We're just seeing blue.
Okay, that's really bad. Let me share the screen again, because we tested this before the start of this seminar, and we didn't have any problem. So let me stop sharing and then share it again. How about now?
Same issue.
Yeah, so we see a big black, we see two sides, right? We see the simulation stuff with the Cedar 355 on the right-hand side, but the left-hand side, all we see is a blue screen.
Okay. This is really bad. So this is a question.
The upper part is, yeah.
How about now?
Yeah, we see it.
You can see the entire thing. So because I want to fit as much code into the text edit. So how about now? Can you see the whole thing?
No, it's good.
Okay, let me move it a little bit.
Yeah, this one is perfect. Yeah.
Okay, you can see it. Okay. Yeah, this is really bad, but I don't have a solution because it should work. So obviously there's some bug in the video client. So all right. So once again, what we're doing here, we have a simple code called atomic.chapel, and it just shows you how we can implement synchronization between tasks in Chapel. So we have a variable called log, and it's an atomic variable, meaning that all processes, all tasks can actually write into this variable, and all of them will succeed. But the outcome of the code is dictated by what is specified explicitly, how we use that variable inside your code. So here we specify the default number of tasks is equal to 5, and it's a variable that we can, obviously, actually we can make it a config variable if we want to override that from the command line. And then we write 0, so we're still running a single task. This is before the call for all loop. So the main thread, the main task writes 0 to this log variable, and then we starting 5 tasks here. So each task prints the greeting from task line and says, I'm waiting for all tasks to say hello. And then it adds atomically 1 to this log variable, right? So log variable is incremented by 1 by each task that runs that code. And then the corresponding task waits. So each task waits for the log variable to become equal to 5. So num tasks is equal to 5. So pause until the variable log is equal to 5, and then only then you can continue running. So only then you can say task ID is done. So let's compile and run this code. And actually, I need to make sure that I also resize the terminal. So oops. So I assume you can see my terminal now. I just resized it.
Yes.
So here, let me compile. And again, I have the make file, but the command you can see right on my screen. So chapel atomic.chapel -o followed by the executable name. And let's just run it. So I'm running it on a inside a 3-core job. So here we go. We have 5, so the default number of tasks is 5. So each task prints out the greetings line, greetings from task ID, and then I'm waiting for all tasks to say hello. And then pause until this atomic variable is equal to 5, and then only then print out task ID is done, and then we finish, right? So this is synchronization point. So in this case, we are making sure that none of the tasks actually get ahead. So if we delete synchronization point, so if I just comment it out, and I will recompile the code. And then I run it, you see there is no synchronization. So now all of them just print out statements, but they don't wait for all tasks to say hello. So this is where now we don't have synchronization. So I'll put synchronization back, and hopefully this is clear how it works, right? So basically we're waiting, each task is waiting for for log to be equal to num tasks, and only then it can proceed. So I'm going to ask you to do an exercise now. Let me paste in the following into the Google Doc. So that's exercise. Exercise number 4 from previous week. And I'll give you maybe 5 minutes on this exercise. So the goal here is to have 2 synchronization points. So suppose we want to add another synchronization point right after the last write line statement, and we add the following few lines. So we add, now we decide to subtract from the log variable, and we are saying that, okay, log subtract. So each task is subtracting from the log variable 1, and then each task is waiting for the log variable to be equal to 0, and then only then it says task ID is really done. So I'm actually going to paste this code into my text editor as well, so you will see right here in the text editor what I mean. So here we have log sub 1, then wait for 0, and then say I'm really done then. So I'm going to give you 5 minutes, and the goal of this exercise is to figure out why this doesn't work. And how this doesn't work, I can actually show you. So let's compile the code. Oh, ID is undeclared. Yeah, I need task ID here. And let's just run it. So atomic, and you see what happens? The code doesn't finish running. It actually logs. So obviously we have a problem here, a bug. So I'll give you 5 minutes to figure out what the problem is. And then you can, if you want, you can turn on your audio or to report back, or you can just paste the solution into the Google Doc. Okay, so the time is up. Does anyone have a solution? I don't see anything pasted in the Google Docs, so let me show you what the solution is. I have a slide on this precise problem right here. So what we have here is a race condition, because we have several processes, several tasks writing into the log variable, into the atomic variable at the same time. The outcome of the code actually depends on which process, which task succeeds first. So imagine that we're running this calculation on two processes. So we have processor 1 on the left, and then processor 2 on the right, and then the code is running at the same time. So on the first processor, let's say we add to the atomic variable to log. So now log is equal to 1 right here, and then we're waiting for log to be equal to 2. So we're waiting for the other task to finish writing into the same log variable. Okay, so we're waiting here. Right? What the arrow right here means. And then at some point, the second task will write into the log variable, so it will add 1 to the log variable. So once this happens, the first task is released from the wait, and it can continue running. So it will print out task 1 is done, and then the next line for task 1 is to subtract 1 from the log variable. And then the next task for the next command for the second task is wait for the log variable to be equal to 2. Right? So depending on which of these highlighted commands in yellow runs first, the code will either behave properly or it will log. So if the subtraction command runs first, then the log variable is now equal to 1, while the second processor is waiting for the log variable to be equal to 2. And if the first command, subtraction, runs first, then, well, the second processor will end up waiting indefinitely, because the log variable will never become equal to 2. And so after subtraction, the first processor is now running the command wait for the log variable to be equal to 0. So both of them entered the indefinite wait for loop. So basically, the first processor is waiting for the log variable to be equal to 0, and the second process is waiting for it to be equal to 2, which will never happen. So this is an example of a buggy code, or how you can use how you can incorrectly insert synchronization and end up with this race condition or a deadlock. So what is the solution here? So the easiest solution is actually to have two separate log variables, and then use the first log variable for the first log condition, and then the second log variable for the second one. So let's do this. Let's modify the line where we define the log variables. So let's have two log variables, log1 and log2. And then we're going to set both of them to 0 inside the main thread, inside the main task. Okay. And then here we're going to say the first condition is synchronization point is log1, add 1 to log1, and then wait for log1 to be equal to num tasks. And then for the second one is, now we're using log variable 2, and I'm also going to add, because it was started from 0, so I'm going to add 1 until it's equal to number of tasks. And then here we have the wait condition. So wait for log2 to be equal to number of tasks. Okay? And then this code should actually behave properly. So let's compile it and run it. And as you can see now, the code actually runs properly with the two synchronization points. So first we have greetings from task, and then after all tasks finish writing this line, then the next line is printed from all tasks. So task ID is done, and then finally we have, after the second synchronization point, task ID is really done. So this is where you actually have to be. So this is fairly low-level parallel programming in Chapel, and when you do things like this, especially synchronizations, explicit synchronizations, you really have to be careful about how you do this. So, and I'm showing this because we're going to use synchronization inside our parallel solver code. So we're going to have two synchronization points, and we're going to do exactly what I just described. We're going to introduce two log variables. So somewhere near the top, before we enter the parallel loop, near the top of our code, let's just say variable define log1 and then define log2, and both of these are integer atomic variables, so atomic integer. And then let's have the synchronization point. So here, right after computing the new temperature, where I say sync point 1, let's have log1, and then we add atomically by each. So each task adds 1 to this atomic variable, and then we're going to pause. So log1 wait for, and now the big question is what we're going to wait for, right? So because each task is writing into the atomic variable, so the number of tasks is number of row tasks times number of column tasks. So here we have to have a product. So we're going to say row tasks times column tasks. So this is what we're waiting for, right? So in the first iteration, we're waiting for the log1 variable to be equal to let's say if we're running it on 12 tasks, so 3 by 4 block decomposition, then we're going to wait for log1 to be equal to 12. And we also need to multiply this by the count, because count, so we're going to do this log check or synchronization every time at each iteration. And then the log variable is going to increase by row tasks and column tasks at each iteration. So we have to account for the fact that it's going to keep growing from one iteration to the next. Okay, so this is the proper wait for condition, and we need to do the same for at the second synchronization point for log2 variable. So here I'm going to say log. Something's wrong with my indentation. Let me check it. Interesting. My Emacs is not indenting properly. So, and then we need to say log2 here. So add atomically from each task 1 to log2, and then each task waits for log2 to become equal to this product, row tasks times column tasks times count. Okay. So here we added explicitly 2 synchronization points. And then we also need to make a few other modifications. So here we have a variable called count, the step counter, the iteration counter. And because now we have, we are running so we're breaking our problem into 12 tasks, and then we have the iteration inside each task. So we need to move the declaration of this counter into each task. So basically, we have 12 iteration counters, and we need to define this variable somewhere here near the top of the each task. So the iteration counter is going to be defined here. There are going to be 12 copies of the iteration counter, 1 for each task. Then I want to make sure that I remove the instance of count right here after I finish at the very end of the code. After I finish my parallel code for all loop, I need to make sure that I don't have the printout of iterations right here. So because here we're printing out counts, and count is going to be, so in this case, actually count is not defined because we just finished the code for all loop, and count is defined only inside the code for all loop. So if we run the code as it is, it actually gave you an error message that count is not defined. So we can either synchronize count and actually compute the total count. That's fairly easy to do. But let's just, to simplify things, let's just delete the reference to count from these statements. So the final temperature at the desired position is, and then print out the temperature. Then we are calculating delta, the largest difference between two successive temperatures inside each task. So we need to make sure, and because that delta is going to be used to calculate, to compare, well, to decide when we need to stop our iterations, we need to actually synchronize delta, and delta will contain, is going to be an atomic variable that's going to contain the largest difference between successive temperatures from all tasks. So we need to have some sort of a reduction operation. So what we're going to do is we're going to define delta as an atomic variable into which all processes can write. So delta is an atomic variable. And then because it's an atomic variable, we cannot actually write into it directly, so we have to use the write function. So here we need to say delta is dot write, so we're going to use the built-in write function for an atomic variable. So we're assigning some large number, in this case 10, tolerance times 10. And then next time we use it, here we're reading the value, so we need to say delta.read instead of just the value of delta. Okay, is greater than or equal to tolerance. Then we also need to define an array of local deltas, and from this array we're going to reduce into the global delta. So the array of local deltas, let's just define it somewhere after we define row tasks and column tasks. So I'm going to say variable array of deltas, and it's going to be array with 12 elements. So from 0 to column tasks times row tasks minus 1. So there are 12 elements. And then it's an array of reals for computing local deltas. Then let's define a local temporary variable somewhere inside the co-for-all loop. So you will see what I will use it for. So variable TMP, and it's a temporary variable of type real. And then inside the while statement, let's set it to right here. Let's set the value of that variable to 0. And then where we're computing the new temperature, we also going to, so we just computed the new temperature, T new at ij, and into TMP, we're going to put the difference between the T new and T at the same point, Tij. So I'm going to say T new ij minus T of ij. And I'm going to take a look at the absolute value. So if it's negative, then you also need to account for that. And then what I really want to do, I want to look at the maximum of this difference and TMP and assign that maximum to TMP. So basically, if the difference between T new and T at this point ij is greater than TMP, then assign the difference to TMP. So initial TMP is 0. So and then we're going to say every delta right after the finish, the end of this small ij loop calculating T news and TMP. We're going to say array delta at task ID, and we're going to store a temporary TMP in there. So the largest difference for a given task is going to be stored as a corresponding element, task ID element of this global array delta. And then at some point when we're computing delta, so right here, I'm going to comment out this line, the old delta calculation, and I'm going to say if task ID, so explicitly run the code on task number 0. If task ID is equal to 0, then, and let's do the following. So we're going to write into delta write, and what I'm going to write into delta, I'm actually going to write not a single value, but I'm going to do a max reduce operation here. So I'm going to take all those local values of array delta from individual tasks, and well, actually, it's not from individual tasks. It's an array that is defined on in the main task, and then each task is writing into the corresponding array element. So now I have these 12-element array delta array, and then I'm going to calculate the maximum element. So this is a max reduce operation, and then we store it as delta. And then also I'm going to put these out statements, so temperature iteration, into this task ID equal to 0 statement, simply because we want only a single task at each iteration to print out something. So I'm going to say if count divided by an out is, so remainder of division is 0, then temperature iteration count is equal to this value. Okay. And I think I'm done. So let's try to recompile this code and see if I made any typos. Okay, so syntax error near TMP line 32. Okay, it's variable. Let's compile again. Syntax error near closing statement line 62. So what did I do there? Right. I need just a single closing bracket. Okay, let's compile it again.
For log 1 and log 2, you don't have the first write as 0?
Yes, so I didn't have the first one write as 0 simply because they are initialized, when they initialize as new variables, their default value is going to be equal to 0. So I could explicitly, to be safe, correct, I could explicitly write 0 before the start of the main of the co-for-all loop. Yes, exactly. But I don't have to do it simply because the default value when they initialize
always
is 0.
forgot that one. Thank you.
The default value is always 0 in Chapel. Okay, so it's compiled. Let's try to run it. So let me run again the, let's see, where did I have it? The base solver, just to remind you that it ran in 12 seconds. Then the first version of the parallel solver ran in 23 seconds. So let's see. So I'm running the base serial solver now. Let's just verify that it's something close to 12 seconds. Yeah, so 12 seconds. And we just compile the new version of the parallel solver. And Let me run it. Okay, so it also took 12 seconds. It actually took slightly longer, as you can see. So what's the deal? So the problem here is that on Cedar, due to its architecture and due to its memory layout on a node, what happens is creating individual tasks is actually quite expensive. So in this case, for this problem size, the parallel code actually takes about the same as the serial code. If you increase the problem size, then you will see that the parallel code will actually start running faster on, let's say in this case, 3 cores than on a single core. Alternatively, what you can do, you can take this problem and try to divide it into a larger number of tasks. And if you have access to more than 3 cores, let's say you start an interactive 32-core job, so covering the entire node, then your code will actually run faster on 32 cores as opposed to 3 cores. But the problem here is that for some reason, starting individual tasks on Cedar takes some time. So we don't see any benefit here. But if we either go to a even larger number of cores, or we scale the problem to a larger problem size, we actually see faster execution. So if I run this exact code on my laptop, where I have 2 physical cores, it actually runs 2 times faster. So in my laptop, it takes much faster to start individual threads. So the reason for that, I don't know. It's something related to architecture, and I don't know exactly. But the bottom line here is the code will run faster if you either run it on a bigger problem or assign a large number of cores to it. So what I'm going to do, actually, a few days ago, I did some testing on 32 cores on Cedar, and I just want to paste the timings into the Google Doc. So at the bottom, I will paste timings. So I run exactly the same problem. Actually, in this case, the code was called parallel 2, not parallel 1. So I ran it on a single core, and it took 32 seconds. I ran it on 4 cores, it took 10 seconds. I ran it on 16 cores, it took 3.8 seconds. And then on all 32 cores, so taking the entire node, it actually took 2.4 seconds, so 2.5 seconds. So you can see the problem actually scales very nicely. It's just there's some overhead with this calculation and for this small problem size, so that you don't see any benefit on 3 cores. But if you go to bigger problem sizes or to larger number of cores, your code will actually run faster. So I'm going to end here and pause for any question, and then we're going to jump on to domain parallelism, the next section. Any questions for this part? Okay, so since there are no questions, let's jump on to part 3. So we'll start by running some single node codes, and then we'll go on to multi-node codes. So as I mentioned at the beginning of the previous session, you can have, so in Chapel supports abstractions for both task parallelism and data parallelism. So data parallelism is a style of programming in which parallelism is driven by computation over a collection of data elements or their indices. So basically, you have a collection of elements in an array or collection of indices in some, let's say, range or domain, and then you organize a for loop that will break that calculation into multiple tasks depending on how many physical cores you have available. So the syntax, let me start a new code, which I'll just call cas.chapel. So starting from scratch. And the syntax for that command is, so it's called a for all command, so index, for all index in some iterand, and then start iterations, and then do something here, so perhaps multiple tasks. So the idea is that Chapel will, you don't specify how many tasks you want to run, like with for all loop. The idea here is that the Chapel will automatically parallelize this loop depending on how many elements you have inside iterand. And then it will break into an appropriate number of tasks. So the appropriate number of tasks is basically given by the problem size and by the number of available cores. So if you're running, let's say you're running on a single, running on a laptop that has 1 physical core, then this loop will always run in serial because you have just one processor available to you. So the same for a serial interactive job. You just have a single processor available, and this loop will always run in parallel. So in our case, on the right side, I have an interactive job that is running on 3 cores. So that means that if my iterand is large enough, if there are more than 3 elements in this iterand, then it will actually run in parallel, and it will use all 3 cores. It will break into 3 tasks, and then each task will do some portion of this for all loop. And then if I'm running this code on multiple nodes, and perhaps on multiple cores on each node, then if my problem is large enough, then I will actually have parallelism across several different nodes and across several different cores on each node. So let me give you an example of a code. So let's say we have a for all, actually let me define some variables first. So let's define set n to 1,000,000. So here we have n is equal to 10 to the 6, and it's an integer variable. As somebody pointed out last week, we actually, so this notation 10 to the 6, 1e6, so scientific notation, cannot be applied to integer variables in Chapel, but what you can do is, so this means what I highlighted here is a real variable, but you can actually convert it, so convert it to an integer variable using this nice notation. So we're defining integer n equal to 1,000,000, and then we can define an array of one-dimensional array of n elements. So the indices go from 1 to n, then it's a real array. So we're defining an array of reals with 1,000,000 elements, and then we're going to organize a for all loop. So I'm going to say for all, and then, so Chapel is case sensitive. What I can do is I can say lowercase for all, lowercase a, in uppercase a, do, and then let's just increment it by 1. So the default value is equal to each element is 0. And then basically what it does, it goes through all elements of the array L, through all 1,000,000 elements, and then it increments each element by 1. And it will do it in parallel. So in our case, we're running it on, if we are to run it on 3 cores, then it will actually break into 3 tasks, and then each task will handle some fraction of the 1,000,000 elements. So most likely it will try to load balance, and each task will do roughly 333,000 array elements. Okay. So I'm not going to run this code because we're not printing out here anything. So if I were to run it, it will just run and will not output anything. So let's just run another code, which that will actually have some useful print statements. So I'm going to declare a count variable, and I'm going to set it to 0. So by default, is going to be because we're assigning an integer variable, is going to be of type integer. And then I'm going to say for all I in, and then I'll have a range from 1 to 1,000, and then with, and I'm going to have some, I'm going to explain what it means, plus reduce operation count, and then I'm going to start a parallel loop. So here's my parallel loop, and I'm going to increase the value of count by I in each task. Okay. And then at the very end, at the very end, I'm going to say right line count is equal to, and then the variable, the value of this variable. So what's happening here is we're starting from with a single task. So in Chapel, you always start whether you're running on a single node, whether you're running on multiple nodes. You always start execution with a single task, single thread. And then we inside the single thread, we're defining the variable count, set it to 0. And then we are starting a parallel loop. So in our case, it's going to run on 3 cores, and then subdividing all 1,000 iterations into loop iterations into onto 3 tasks. And then each task is going to have its own copy of the count variable. And the reason for this is because we have the plus reduce count statement here. So each task will have its own value of count, and then it's going to increase it by I in the corresponding iteration. And then so we're going to have 3 loops being computed in parallel for some subsections of this range, 1 to 1,000. And then when they finish, they're going to synchronize. And then they're going to take, so Chapel will take the value of count from each of the 3 tasks and then add them up together. So that's what the plus reduce statement means. So take the local values of count and then reduce them to a single count using the plus operation. So take all those individual counts and then add them up to compute the total count. So let's compile and test this code. So when compiling, by the way, notice that I'm simply saying Chapel test.chapel -o test. So I'm not using the --fast optimization here, and this is simply because I have such a simple code. I don't really care how long it takes. It only takes a small fraction of a second, so I'm just going to compile it without the dash fast flag. So here we go. Here we have count, and then it says count is equal to 500,000, and what this is, this is simply the sum of integer numbers from 1 to 1,000. So we computed the sum of 1 to 1,000 using a parallel loop. Okay. Any questions at this point? Okay. Then let's make a small modification. So let's first, this line which says count, where we're increasing the counter, we're going to modify it. So instead of saying count plus equal to I, we're going to say simply assign the value of 1 to it. So here we go. Count is equal to 1, and then here we're going to say actual number of threads is equal to count. So what we're doing here now is we have these 3 parallel tasks that each task is simply has the same value of count is equal to 1, and then we are reducing these 3 values to a single value by computing the sum. So basically, effectively what this will do is it will report back the total number of threads that this code ran on. So let's do this. Let's compile the code again. And then let's run it. So because I ran it in a 3-core environment, it actually printed back actual number of threads or tasks is equal to 3, which makes sense. So basically, we have a sufficiently large range from 1 to 1,000 that was broken into 3 parallel tasks, and then they ran in parallel. And then finally, we are printing out the number of tasks. So let's do a quick exercise. This is slightly more complex. I'm going to give you 10 minutes for this. And the exercise is the following. So actually, let me bring the slide for this exercise. So the exercise is to compute pi using data parallel for all loop using these formulas. So basically, try to compute the integral from 0 to 1 of the function 4 divided by 1 plus x squared. And so you use I don't know, simple Simpson's rule. So basically divide it into n elements, this interval from 0 to 1 into n elements, and then calculate the value of the function inside each element, and then sum them up and divide by the total number of elements. Okay, so simple rectangular Simpson integration, and then that will give you the approximate value of pi. So I'm going to paste this exercise into the Google Doc. And it's going to be called exercise 1 because we just jumped into the new section. So here we go. I just pasted it at the bottom. So using the first version of for all Chapel code, actually in my case it's called test.chapel. So let me bring back the old version. So we have count is set to increment by I, the loop variable. So using this, what you see on the screen as a template, try to write a parallel code to compute pi. And I'm going to give you 10 minutes for this, and then I'm going to do this exercise on the screen.
Alex, can you give the non-parallel algorithm for this?
Sure. You mean for calculating pi? For calculating pi?
Yeah.
Okay, sure. I can certainly do it. So I will write it right into my text editor, and then, well, so the problem with this is once you see the serial code, it's very, very easy to write the parallel code in Chapel because you essentially don't have to do anything. But yeah, I'll do it. So what I'm going to do is I'm starting. So imagine that this is a new code right after this line. So I'm going to say I'm going to say config and then define the number of intervals to set it to 1,000. And then because it's a config variable, I can actually override it from the command line. Then I'm going to say variable age is going to be the width of my subinterval. And then the total is going to be the sum of, well, the integral, the output. And both of them are going to be of type real. And then I need to calculate h. So h is going to be 1 divided by n. So that's the width of the interval. Actually, subinterval width. Okay. Then I'm going to write the serial code. So I'm going to say for I in 1 to n. And then I'm going to have the loop here, and then here I can define the variable x. That is going to be the point at which I'm estimating function. So x, I'm going to simply position all of these equidistantly. So I'm going to say x is equal to h times I minus 0.5, so they actually fill the interval symmetrically. And then I need to calculate the value of the function at the point x and then add it to the total. So I'm going to say total is incremented by 4 divided by basically the value of function. So 4 divided by 1 plus x squared. And then here I'm printing out the intervals. I'm going to say, the answer. I'm going to say pi is, and then the value of total. And then you need to make sure that you subdivide it by the number of intervals, or equivalently, you can multiply it by the value of each. And here's my entire serial code. So you need to make it parallel. Yeah, good question. How we can print out more digits in write? So the syntax for that, you can actually use a C-style write statement in Chapel. And the syntax for that is not obvious. I'm going to show you. Pi, what you can say is, so instead of write command, you can say write F, so that's formatted right. And you can say pi is $, and then specify how many digits you want. So I'm going to have 3 digits before the decimal point, and then 10 digits after the decimal point. And then the trick with write F command is that it doesn't automatically return the end of line command. So you actually have to specify end of line command explicitly. So this is C-style formatted right. That simply we can simply specify how many significant digits you want before and after the decimal point. And here, by the way, I just had to restart my job simply because I specified 1 hour, and we are past 1 hour now. So the job was killed, and I just restarted another job inside reservation. So I'm still running on a single node and 3 cores. Okay, so I'm going to show you the solution because you already have the serial code, and it's really a couple of very small modifications that you have to make to this code to actually make it data parallel. So what you need to do is just modify 2 lines. So the first line is going to be changing for loop to for all loop. So that's actually data parallel loop. And then the second modification, actually in the same line, you need to add the reduction statement. So you need to say that once we calculate all those local values of total in each task, you need to reduce them to a single value using the plus operation. So plus, reduce, and then total. And that's all. So that's the entire parallel code. And of course, I need to delete the first one, the first code. So let's just compile and run this parallel code. So I'm going to say make test and then run it. Okay, so cannot iterate over values of type real integer. Ah, interesting. So what do I have here? For all I don't see any problem here. So plus reduce total. Type real 64.
Is the total supposed to be plus equal or just equal in this case?
No, it's supposed to be plus equal. It's incrementing. So I'm just trying to decide why. I don't see an obvious error here. So let me try to save it. Maybe I just didn't save it in time.
Is it incrementing and then reducing on a plus?
Yes, on the total. Yes. So because we want to calculate the total sum over all points. So we take a range of points, and then we're subdividing that range into 3 small ranges. So we're calculating the sum for each one of these sub-ranges. And then we have 3 sums, and then we are reducing these 3 sums to a single sum. So that's why we have plus reduced total. And here we also have plus equal to. So the problem is I cannot iterate over values of type real. So the problem is actually with I, but I don't see. So here we have. I know where the problem. But wait a second. No. Roll I in 1 to n plus reduce total. No, I don't see the problem. So that's weird.
Someone wrote.
Sorry?
Someone wrote maybe what could be the problem.
Don't declare variables x inside the loop. Okay, right. Don't declare x inside the loop. Okay. don't think that's a problem.
Do you need to make sure that n is an integer? Or does that happen automatically?
Where exactly?
At the very beginning, you have a config constant n, right?
Yeah, but it should be integer because 1,000. I'm just using the value of 1,000. So let me try this again. I don't see an error. So let me paste. So I ran this code before, and let me just copy and paste the code from my notes and see if it runs. And then we'll try to find the difference there. So make test. Okay, so this one works. So what's the difference between the two? I don't see. I don't see. It's a typo somewhere. So a weird character, but I just don't see any difference. And this works, unless anybody can see a difference. So the with statement. Oh yes, of course. Yeah, I missed this. Sorry, I missed the with statement. Yeah. So when we're doing reduction, we need the with the with statement. So excellent. Yeah. So that was the problem in the original code. So let's just go back to the original code, and of course I'm not using the right syntax. So with. So we're doing the for all loop with the reduction. So this is the proper syntax, and I was missing the with statement. Okay, and now it ran. So let's just run it on. Oops. Invalid argument can't find the end of conversion specifier.
The R is missing after the 10. Yeah.
Oh, yes. Yes, for real. Yeah, exactly. You see, when I'm doing live coding and trying to type fast, I miss a lot of things. So yeah, the R was missing. So when you're specifying the formatted output format, you need R here to ensure that it's printed as real. And then here we go. So here we have the approximate value of pi computed using 1,000 intervals. So let's just play with that number. Let's use, instead of 1,000 intervals, let's use 100 intervals and see if the answer changes. So as you can see, the answer is less accurate. With 10, it's even less accurate, and so on. So if we take a larger number, then it's going to be more accurate, which makes sense. Right? So you can modify the value, override the default value of the configuration variable from the command line. Okay. Any questions? If not, then what I'm going to do now, I'm going to copy and paste another version of the task parallel code to compute to do the heat transfer solver, and I'm going to only paste the lines which are important for task parallelism, so not the entire code, just to show you how this can be done with task parallelism on a single node. So what we have here is we are subdividing our problem. So initial array is 100 by 100, and then we are subdividing into 12 blocks, so same 3 by 4 decomposition. And each block has 34 rows and 25 columns. And then the last row and the last column of blocks is actually a little bit smaller, so the total is 100 in each dimension. And then we're simply doing this for all, so parallel for all loop. And I'm using the interesting syntax in tuple here, which actually produces two nested loops. So one is for variable R, the other one is for variable C. So I'm showing the Google Doc now, where R runs from 1 to rows and C goes from 1 to columns, so we're covering the entire array. But now we are doing this coverage, so we're doing this for all loop with a step, and the step is, so for rows, it's row stride, and for columns, it's column stride. So basically, we are going, so I is equal to 1, then 35, then 69, and the same for columns. And basically, we're making sure that the entire array is subdivided into these 3 by 4 blocks. And then for each block, we are running, so what's inside the for all loop is actual calculation for a block, and then we have a nice single line calculation of the starting and ending indices for each row number and each column number, and then we simply update the temperatures. So here you see that this is different from, so let me go back to the parallel loop. So there I had in the previous, so what we did an hour ago, we had task parallelization, and we explicitly specified the number of tasks. So in this case, 12. And here we are looking, we're doing data decomposition. So we're doing the for all loop where where Chapel subdivides our problem into the appropriate number of tasks at runtime, even looking at how many physical processes we have access to, and then it simply adjusts that to the problem size. And this is another way to implement our calculation using data parallelism on a single node. But of course, what is interesting in Chapel is that you can actually write distributed memory problems. So you can actually scale to bigger problems by subdividing your problem into tasks that run in parallel on several different nodes at once. To make this work, you actually need a multi-locale Chapel setup. And on the cluster, we already have this inside another Chapel module, which is called Chapel. Let me see what it's called. Chapel multi-seeder. And to load it, so I will exit my interactive job now because this is a single node interactive job. And I will unload my current Chapel module. So my module is called Chapel -single / some version number, and I'm just going to omit that version number. So simply say module unload Chapel single, and then I'm going to load the multi-locale Chapel module. So I'm going to say module load -multi -seeder, and then I will specify the version number. So here I loaded the multi-locale Chapel module, which is installed on seeder cluster. And it's actually, so if I do which Chapel, so to see where the Chapel compiler executable is sitting, it's actually sitting inside that opt software subdirectory. And then I also need to start the job. So I'm going to start it as part of the reservation. So exactly the same command as before. But the difference is I'm going to specify not a single MPI task, but I'm going to explicitly say on how many nodes I want to run this job. So I'm going to ask for 4 nodes and then 3 CPU cores per node. So the syntax is slightly different. Instead of number of tasks, I'm specifying the number of nodes. So I'm running this as an interactive job on 4 nodes, 3 cores per node. So that will give me in total 12 cores, and everything else is the same. So asking for 1,000 megabytes per task per CPU essentially. And let's just wait for this to get started. So we started the job. Okay, requested, not available. Maybe because my reservation finishes so I assume. So let me try 40 minutes. I don't see an obvious problem here. So I'm asking for 40 minutes in the last run on 4 nodes. Yeah, -- nodes is equal to 4 CPUs per task is equal to 3. And then I'm not sure what the problem is. Camille, are you still there? Can you see the problem?
Well, you're asking for nodes and tasks. So you're asking for 4 nodes, but it doesn't say how many tasks per node.
It's a single task per node, so that's the default value.
Yeah.
This exact command should work. So I've run it many times. So the default value is 1. So let me just paste it, unless I make some obvious typo. What I'm going to do, I'm just going to paste the command from my nodes and see if that runs. But it's exactly the same one. So I don't know what the problem is.
Request a node. Unless there's not enough resources?
Yeah. So if everybody, but we are supposed to have, I think, 10 or so nodes here inside this reservation. Let me ask for 2 nodes so you see if that changes. Yeah, probably not enough resources. So I guess maybe a lot of people are watching this via the web stream and just running this. I guess, I don't know. But yeah, it looks like there were just not enough resources. So. Okay, so while the job is starting, hopefully it will start, I'm going to go back to my test code, and I'm going to erase everything I have here. And then I'm going to have the following write line command. So I'm going to print out the built-in locales array. I'm just waiting for my job to get started. I will exit Cedar and then log in back in. And what I'm going to do is load the chapel module once again. And then I'm going to ask for 2 nodes once again and see if it succeeds this time. Oh, there are only 2 nodes in reservation, says one. So I probably made a mistake configuring reservation yesterday. Oh. Let me verify that. So exactly. I made a mistake yesterday configuring the reservation. So what's the easiest way to correct that? I just don't know which nodes. So I have a list of nodes. Actually, here I have it. Yeah, I'm gonna do it. Yeah, I have the list. Yeah, that's my mistake.
Yeah, you won't be able to get new nodes for another 3 hours.
Oh, even if I reconfigure the reservation?
Most likely. Well, unless new jobs are ending, right?
Okay. So should I try it or should I just abandon it and run on the resources I have? I don't know. Does it make sense to try to run S-control command again?
You could try. Do you have permission to do it, though?
Sorry? Yeah, I do have permission.
Okay. So you
So
can
let me try. And, oh, okay. No, I cannot modify it because it already started.
Yep.
Okay, well, I will work with what I have. So I'll just start again. Hopefully this works.
Yeah. It wouldn't work anyway because you're specifying specific nodes.
Mm-hmm. Okay. Oh, that was my mistake. Reconfiguring, adding users yesterday, and I just by mistake specified the wrong number of nodes. So it works for me now, but most likely, well, some of you will be able to run because I'm asking only for 3 cores per node. But if there are a lot of participants, maybe somebody will get an error that there are not enough resources, but we'll work with what we have. So let me see, do I have my module, chapel module loaded? Yep, it's a multi-local chapel module, and I can actually verify it by running the module list command. And yep, chapel multi-local multi-city is loaded. So what I'm going to do is go into my temporary directory where I have all the codes. And here I can actually verify, check whether I I'm running on, well, my environment. So I'm going to ask for the a list of nodes. So I'm running on 2 nodes in this case, and also I'm going to print out the number of CPUs per task, and that should be 3. Yeah. So in total, I have 6 physical cores available to me, and I need to set up 2. So to be able to use parallelism inside Chapel in this environment, I need to set up 2 variables. So the first one is HPI node CPU affinity, and it's needed to enable task parallelism inside each locale, inside each node. And then also want to limit how many threads we can start per node. So we need to set that variable. So basically, I'm saying Chapel, this variable, the one that I highlighted here, is equal to in our case 3, so that when we run parallel Chapel codes, they don't spawn the entire node, but they will only be limited to the actual number of tasks we have at our CPU cores we have at our disposal. So in any case, let me compile and run my code. So let me make sure that, so I do make clean, I erase all executables, so there's no executable now. And I'm going to simply say Chapel, test.chapel minus O test. So we'll compile it. And then when I do ls, you will see that now I actually have, because I'm using a multi-locale version of Chapel, I will actually end up with 2 different executables. So one is called test, that one is called test_.real. So test_real is the real machine executable that contains my code, and test contains the launcher for this code. So what it means is that when you actually install and configure a multi-locale Chapel, there are many ways of doing this. So this particular version of multi-locale Chapel on Cedar was configured with a launcher to start it inside a Slurm job using the OmniPath interconnect. So there's actually a lot of low-level setup that I have to do, but fortunately, we already have a module for you. But once you load the module, the important thing here is to make sure that these 2 variables are set, and then you're all set up to run your parallel multinodal Chapel codes. So we compiled our code. Let's just verify that it's compiled, and let me run it. So when I do it this way, you see that it actually asks me to specify the number of locales. And I need to specify how many locales I'm running. So the maximum available to me is 2, because I have only I have this as introductory job on 2 nodes. And so here I'm running a 2 on 2 nodes, on 2 locales. And this built-in locale array in Chapel actually stores the names or the indices of the names of the locales. So they're called locale 0 and locale 1. Okay. So I can actually write code to cycle through this locale. So what I can do, I will keep adding to my code. I'll say for locale, for loc in locales. So as you can see, this is very similar to Python syntax do. And this is a serial loop, because we're using a serial for loop, right? So it's not a parallel loop. And then on a given locale, do, so runs on a given node. And then let's just print out a statement right line, and then I'm going to say this locale is named. And then here, what I can do, of course, I can simply say log, and that will reference, that will give me either locale 0 or locale 1, but I can actually probe the actual name of the node from Chapel. So what I can do is say here dot, and in Chapel here refers to the locale on which the code is running. So this is a Chapel object that contains a number of built-in functions and built-in attributes. So what I can say, I can actually reference the name of the node using these notations. So here dot name. So once again, here refers to the node on which this code is, this particular line is running. Okay, and then I'm simply printing out its name. So let me recompile the code again.
So I have a question.
Yep.
It's possible for both of your tasks to be, in Slurm to be on the same node. If you ask for node equals 2, tasks equals 5, and we have 32 core nodes, you can end up on the same node.
Can I?
Yes. So the name will be the same?
Yes, if you're on the same, well.
Because unless you specify that you don't want them to be on the same node, you will end up on the same.
I don't want them to be on the same node.
You can end up on. to be on the same node?
I can. Okay, I'll need to look into this. I don't know the answer to your question, but in this specific case, I don't want to be in a single node. So I don't know what will happen if you run it on a single node using this syntax, this travel syntax. Okay. So let me run this. Okay. So you see this locale, and actually I have a typo there. This locale is named, and then I have the full name of the node. So I can actually print out the shorter version of the name. So I'll simply subset the string, and I will only print out the first 6 characters. So let me recompile. And this is going to be useful later on when we look at domain decomposition, and then each element will store the name of the corresponding of the locale. So the corresponding line is running on. Okay, so this locale is named Cedar 355 or Cedar 357. So let's try to make this a parallel loop. So all we have to do is simply modify change for to for a loop, and then we need to recompile the code, and then the code will actually run in parallel. So for all, lock and locales do, and then on each locale do something. And now when I run it, the code actually runs in parallel. And you don't see any obvious difference in the output because we only have 2 locales. But in principle, these can be run in random order. So whichever line is going to be printed first really depends on the runtime environment. So because we're running it simultaneously, so the write line command runs simultaneously on each locale, and in advance you don't know which one is going to be printed out first. Let's try to do something a little bit more complicated. Let's use a module called memory to have access to, to probe memory environment on each node. So we're going to say for, and actually I'm going to revert back to the serial for loop. I want to revert back to the serial for loop so that all statements appear in the same order. So I'm going to say serial for loop, go through all locales, and on a given locale, do the following. And I'm going to write a bunch of commands here. So I'm going to say this locale is named, and then the name of the locale, and then I'm going to say write line. It has, and then I'm going to print out the number of physical cores. So the function for that is here dot number of processing units. Cores. And then, and then write line and also I'm going to print out physical memory. So here dot physical memory unit in memory units in gigabytes, and then return type real. Gigabytes of memory. And then I'm also going to print out the maximum parallelism that is available to us. So the variable for that is here dot max task parallelism, and then I'm going to say available cores. Okay. So let me try to compile it. And run it on 2 cores, 2 nodes, on 2 locales. And here we go. So this locale is named Cedar 355. It has 32 cores, physical cores, 125 gigabytes of available memory. So this, as you notice, doesn't show us the memory available to us. It's actually the physical memory on the node, 128 gigabytes, minus whatever is taken by the operating system and by various utilities running running at the time. So 125.8 gigabytes is available physically to all tasks running on this node at this time, and then 3 available cores. So as part of our interactive job, we only can access three cores at a time. Okay.
Pedantically, you get the amount. You're only allowed to touch the amount of resources that you request in your Slurm
Yes.
job.
Yes, correct. Yes. If you try to use, for example, more memory, then your job will be killed. Correct. Okay. Let me comment this out and jump into domain parallelism. Oops. Let's recall the definition of a range in Chapel. So we covered it very briefly in the first section. I mentioned there are ranges in Chapel, and I think I showed some examples, but let's just do it formally. So in Chapel, you can define a range, which is a one-dimensional set of integer indices that can be either bounded or infinite, unbounded. So let me show you an example of a bounded range. So let's say from, I'll call a variable 1 to 10. And it's going to be a bounded range, so of type range, and then from 1 to 10. So basically, this is a set of numbers, 1, 2, 3, and so on until 10. Okay. We can also use variables in definition of a range. Let's see, 123, A is equal to 123, and B is equal to 456. And then we can say variable A to B, that is the name of my range, and I simply say range is equal to A to B. So in this case, I'm using the variables as the range brackets. So you also can have a range with a stride. Let's say we have a variable called 2 to 10 by 2, and then it's a range that is stridable. Stridable is set to true, and then we can see that it's a range from 2 to 10, but with a step of 2, so by 2. Okay. And finally, an example of an unbounded or infinite range. So 1 to infinity, and it's a range of integer numbers from 1 to infinity. So in this case, it's unbounded. So these are ranges. So ranges are always one-dimensional in Chapel. On the other hand, Chapel also has an abstraction for domains. So domains are multidimensional sets of integer indices that are always bounded. So let me show you an example. Let's say we have a domain that I will call 1 to 10, and it's a domain of integers. It's a one-dimensional domain. So multidimensional domain can still be one-dimensional. And then Chapel uses curly brackets for domain domain interval. So 1 to 10 is a one-dimensional domain of integers from 1 to 10. So let me give you an example of a two-dimensional domain. So I'll call it 2 dems. And so it's a two-dimensional column, two-dimensional domain where the indices, the first index runs from -2 to, let's say, 2, and the second index runs from, let's say, 0 to 2. So this is a two-dimensional domain. We can also define a third dimension as a variable. So for example, I can say third dimension is a range. So it's a range variable, let's say from 1 to 16. And then I can say that three-dimensional, so 3 dems, three-dimensional domain called 3 dems is a three-dimensional domain. And it's equal to, let's see, 1 to 10 in the first dimension, 5 to 10 in the second dimension, and then we can simply use the range for the third dimension, closing with curly brackets. And so the nice thing, let me just compile this code to see if because I will keep adding to it, to see if there are any syntax errors or typos. so there are no typos. The nice thing about domains is you can actually cycle through its elements. So you can see for, let's say, index in 2 dimensions, and then do or curly brackets, and then just write out the corresponding index. So index, and then I'm going to add a space after that index, because instead of write line, I have just the write command. And then let's just advance the insert the line break. Okay. So we're simply saying so it's a serial loop for index in 2 dimensions. We're cycling through all elements, all indices, all points in this 2-dimensional domain. Let's just see what happens when we run this code. Number of locales. So I'm going to run it on a single locale first. Single node. So here we go. As you can see, we have a 2-dimensional domains, and index simply refers to a tuple of indices, I and j, that we don't have explicitly in the code, and then it goes through the entire 2-dimensional domain. And we can also access these indices explicitly. So we can say, for example, for x and y in 2 dimensions, so that 2-dimensional domain, and then say do, because we have a single line, and then I can say write, and then I'm just going to print out x, then comma here, then y, and then let's have bigger separation. Okay, so I'm printing x and y explicitly. So need to compile it first. Let's run it on a single locale. And as you can see, we actually access the indices, x and y indices, explicitly in the chapel code. But the end result is the same. We're going through all points in this 2-dimensional locale. So let me comment out this code, and we'll just keep adding to the code. Let us define a 2-dimensional domain of size n squared, so n by n. And I need first to define n. So I'm going to say constant, n is equal to constant. Config constant n is equal to 8, so it's a configuration variable that can modify from the command line. And then let's define a constant mesh. That is going to be a 2-dimensional mesh, and then it's going to cover the indices from 1 to n in both dimensions. So it's an n squared mesh. And then let's go in parallel through all mesh elements. So for all m in mesh, do, and then let's print out. So let's print out m, the index, then have some space. Then let's print out the locale where that where that element is stored, where that index element belongs. So m.locale refers to the node or locale on which this mesh element is stored. And then I'm going to print out the ID of that locale or of that node. Then let's have some space, and then also print out the ID of the locale or the node on which this line of code is running. So here in Chapel, always refers to the locale on which this line is running. So here the ID of the node on which line is running. And then let's just print out maximum parallelism. It's going to be the same, all of them. So here dot max task parallelism. And let's compile this code. So we're cycling through all n squared mesh points, and then on each number of locales. So let's run it on a single locale first. So here we're going through all n squared points, 64 lines, and for each line we're printing out the corresponding mesh elements, so I and j. And as you can see, this is a parallel loop because they're actually not in order now. They are running in parallel. And then we're printing out the ID of the locale on which that element is stored, so it's all zeros. then we're printing out the locale or the node, the idea of the node on which this line is computing. So that's all zeros as well. And then the maximum parallelism is always 3, because in my case I'm running inside an interactive Java in which I have only 3 cores per node. So let's run this on 2 nodes and see if it makes any difference. And for 2 nodes, it's exactly the same. So I ran it on 2 nodes, minus L2, and as you can see, the locales, the idea of the locale on which that mesh point is stored and on which the line is computing is still 0 and 0 respectively. So this code, this is a parallel code, but this code is running on a single locale, because we did not specify, we did not specifically ask Chapel to start a task on a different locale, so using the onLoc syntax. And we also have the mesh that is stored explicitly on, it's not a parallel mesh, it's stored in shared memory on a single node. So the beauty of Chapel is that you can actually you can actually distribute meshes among several different nodes. So before I go there, I'm going to show you how you can define arrays on top of meshes. So let's define an array of temperatures. I'm going to call it capital T. So it's defined on top of the mesh, and it's going to be of type real. So this is array of temperatures on top of our mesh. And then I'm going to comment out this line, and I'm going to cycle through all elements of array T in parallel. So I'm going to say for all lowercase t in uppercase T do, and then let's just print out the corresponding value of T. So you will see that it's 0 because we're printing the element now, element of an array, and then have some space, and then print out the locale, the idea of the locale on which that array element is stored. Okay. So let's compile and run it. Running this on 2 locales. And as you can see, I get very similar output. So all array elements are zeros because we just initialized the array. We didn't assign anything on 0 to it. And also, all array elements are stored on the first locale. So, and this is because we didn't distribute our locale across different nodes. So in Chapel, you can actually define a distributed domain. So the idea of a distributed domain is that it will be stored on in shared memory on more than a single node using the distribution that you specify. So Chapel has a number of probably a couple of dozen, maybe a dozen, a couple of dozen of different distributions. So I'm going to show you 2 today. So the first one is block distribution. And to use it, you actually have to load the corresponding module, so block distribution. And this is, so use standard block distribution, simply distributing our array elements or mesh points in the same way we are distributing them dividing them among tasks in when we're looking at task parallelism. So it's basically an n by n decomposition. You will see what I mean in a second. So our array size is going to be n by 8. We're going to define a local mesh, so of a two-dimensional mesh, 1 by n, and then we're going to define a distributed mesh. So I'm going to call it distributed mesh, and it's going to be a two-dimensional domain. And then I'm going to say it's going to be mapped to locales using a block distribution. So block, and then I need to specify the bounding box. Bounding box is equal to mesh. I'll explain what it means in a second. And then is equal to mesh. Then we define, let's define an array called A on top of this distributed mesh. So because the mesh is distributed among several nodes, the array is going to be distributed in exactly the same fashion among the several nodes. And then I'm going to have, instead of an array of reals, I'm going to have an array of string variables. And then I'm going to cycle through all elements of A. So I'm going to say for lowercase a in upper A case, and then do something. And I'm going to assign, so what I'm going to do, I actually use each element of A because it's a string. I'm going to use it to store the several properties, several interesting attributes. So the first one is going to be the ID of the locale on which that element is stored. Okay, so A.locale points to the locale or the node on which that value is stored, and then .id will simply print out the ID of the locale. So we store it as a string, and also we add so some separator. Actually, let me add dash separator, and then let's also store the ID of the locale on which this line is computing, and I want to use the short version. So plus the separator, and then let's just for the kicks have the again the maximum parallelism. So here max past parallelism, and then let's have a longer separator. And then finally, so this is a parallel, actually this is, sorry, we need a parallel loop, of course, for all, because we're going in parallel through all elements of the array A. And then finally, let's just print out the entire array using the usual standard write line command. So let's compile this. And let's run it onto nodes. Actually, what I want to do is let's have a shorter separator so that the whole thing fits nicely on the screen. Let's recompile it. So running on two locales. Here we go. And hopefully you can see the output on your screen. So what we have here, so remember that we're printing out three numbers. The first number for each array element is where that array element is stored. So as you can see, that array element is subdivided between locales 0 and locale 1 using a block distribution. So here I have a one-dimensional decomposition. So the first four lines are stored, the first four rows are stored on node 0. The second four rows are stored on node 1. So if I were to run this on 4 locales, then by default it will use the 2x2 decomposition. So the upper left corner will be stored on locale 0, upper right corner on locale 1, lower left corner on locale 2, and then lower right corner is going to be stored on locale 0, 1, 2, and 3. Right? So 0, 1, 2, and 3 correspondingly. But right now I have access only on, because I misconfigured the reservation yesterday, I have only access to 2 locales, 2 nodes, and you can see where each element is stored. Then we are printing out the name of the corresponding of the locale where the line is computing. So not where the element is stored, but where the line is computing. And as you can see, it's for all of them, it's exactly the same. So CEDA 355 is node 0, CEDA 357 is node 1. So you can see that computation happens on the same locale on which the corresponding array element is stored. And then finally, we're printing out the maximum task parallelism, which is 3 in our case, because we reserved only 3 cores per node. So you can see this is actually a very nice way of testing how our array is distributed among nodes, locales, when we define it on top of a distributed mesh. So the core concept here is that first you need to define a distributed mesh right here, and then you define a distributed array on top of this mesh, and the array element is going to be distributed in exactly the same way as the underlying mesh. So the syntax that I'm using here is slightly obscure. So what it means is that we are using, so where mapped means that we are mapping these two-dimensional locale to the 2 locales. So block bounding box mesh means that we do not have any elements outside. So basically it means that the edges of our domain are specified by the mesh domain. So we don't have any points outside of that actually, let me bring up the very last slide. Outside of that decomposition. So here's the picture on the left, shows the decomposition. So it's a 3x3 decomposition among 9 locales, and we don't have any ghost zones on the outer edge of this decomposition. So on the other hand, if we were to do the following, well, so let's say dmapped block bounding box equal to mesh, and then we specify a bigger domain, let's say from 0 to n+1 in each dimension, n+1 in each dimension, then this will produce an additional layer of ghost zones on top of our decomposition. So the layer of these ghost zones will only sit on the outer layer of our node. So in this case, a 3x3 decomposition. These ghost zones will not be on the inner node, but they will be present on the outer node. And this is useful for specifying boundary conditions, or for all sorts of tasks. So this is just an idea of how we can specify a bounding box, the edge of the array, which is different from the outer edge of this array. Okay. So because we are running out of time, what I'm going to do now is I don't have time to go through all the examples and exercises, and most importantly, writing the domain parallel version of our heat transfer problem. I'm going to paste the notes for the link to my lesson notes. So if you go to the Google Doc, I'm pasting it right now. So lesson notes, right at the top of the Google Doc, right there. And I'll make it a clickable link. And if you open that page, you will see all the notes for today's session. And unfortunately, I had time only to cover a small fraction of the data parallel material. But there is so everything I was going to say is, and all the code examples are actually in there. So let me drag this window to right here, so you can actually see it on my shared screen. And by the end of today's section, if you go through all these examples and all these exercises, you will actually have a domain parallel, well, both distributed memory and shared memory parallel code that will be able to run on multiple nodes in parallel. And then if you do timing, you can actually see that, so in this case, if we're running on a smaller problem size, it actually, so the parallel version of the code runs slower for a small problem than a serial version of this code. And the reason for this is because there is communication overhead, so you have to account for the fact that it takes some time. So underneath, Chapel really uses MPI, to message passing interface, to send messages, so all data between to exchange ghost zones and so on between different nodes. And that has some overhead. But of course, if you scale to a larger problem size, so in this case, going to problem size 650 squared, so rows and columns, and this takes about the same time on one node and on 4 nodes. So you have, still you're not really gaining anything from running parallel code, but when you go to bigger problem sizes, so in this case 2,000 squared, then it actually runs significantly faster when you run on 4 nodes as opposed to running on a single node. And here is the final version of the data parallel code that runs in both uses shared memory parallelism and distributed memory parallelism. So it's actually an efficient code that runs very, very nicely on a cluster in a multi-node environment. So that's all I wanted to say today. Well, except that, of course, I didn't have time to cover a lot of material, and there are exercises here as well. So if you're curious, you can certainly do it on your own time. And so these are designed to really guide you through different concepts of data parallelism in Chapel.